This time, we're finally getting to the most massive, the most compact, and truly the most bizarre objects in the entire universe: black holes. These remarkable cosmic phenomena are the final triumph of gravity over matter, the ultimate victory of one of nature's fundamental forces. They represent the ultimate end states of the cosmos, the final horizons into absolute nothingness, the edge of what we can comprehend. Let's take a closer and more detailed look at exactly what these extraordinary things are, where they come from, how they behave, and how they came to captivate and challenge our understanding of the universe and the laws of physics that govern it. Black holes challenge our intuition in almost every way imaginable. They're places where gravity becomes so strong that it literally breaks our everyday understanding of space and time. They're regions where the universe itself seems to fold in on itself, creating boundaries beyond which we cannot see or communicate. And yet, despite their mysterious nature, they follow precise mathematical laws that we've been gradually uncovering over centuries of scientific investigation. The study of black holes has united different branches of physics in unexpected ways. Astrophysicists observe them in the sky, general relativists calculate their properties, quantum physicists ponder what happens at their cores, and information theorists debate what becomes of the information that falls into them. This convergence of disciplines around a single class of objects is rare in science and speaks to how fundamental black holes are to our understanding of nature. To truly appreciate black holes, we need to understand that they sit at the intersection of the very large and the very small, bridging the cosmic scale of galaxies with the quantum scale of subatomic particles. They force us to confront the limits of our most successful theories and push us toward new physics that we've only begun to glimpse. They are laboratories of extreme physics, natural experiments that test the foundations of reality itself in ways we could never reproduce on Earth. First, we're going to learn about the fascinating and surprisingly long history behind black holes, a history that stretches back further than you might imagine, well before we even understood what they truly were. Back in the year 1783, a brilliant scientist and clergyman named John Michell sat down and carefully studied Isaac Newton's groundbreaking ideas on the fundamental nature of gravity, ideas that had revolutionized how we understood the universe. He was actually the very first person to seriously consider the idea of something resembling what we now call a black hole, even though he wouldn't have used that name. And even though his understanding was limited by the physics of his time, Michell was a remarkable figure in the history of science. Though he's not as well known as he perhaps should be, he made contributions to geology, magnetism, and astronomy. He was also a skilled instrument maker and even invented a method for manufacturing artificial magnets. But his speculation about dark stars stands out as perhaps his most prescient contribution to science. He took very seriously Newton's corpuscular theory of light, a fascinating idea from that era. That was the intriguing idea that light itself was not a wave, but rather was composed of a stream of tiny particles. Particles that traced straight rays from some luminous source out into the universe. I described this particular idea and its evolution in much greater detail in my video series on the history of science, if you're interested in learning more about how our understanding of light changed over the centuries. Michell combined this particle theory of light with Newton's well-established theory of gravity, which described how masses attracted each other across the vastness of space. He then imagined an object he called a dark star, a theoretical object unlike anything that had been observed. In the November 1783 edition of the Philosophical Transactions of the Royal Society of London, one of the most prestigious scientific journals of the time, he stated something quite remarkable and prescient. If there should really exist in nature any bodies whose density is not less than that of the Sun, and whose diameters are more than 500 times the diameter of the Sun, since their light could not arrive at us, or if there should exist any bodies of a somewhat smaller size which are not naturally luminous, of the existence of bodies under either of these circumstances, we could have no information from sight, yet we ought not to conclude that no such bodies exist. In other words, there could be massive objects out there in the universe that we simply cannot see. Mitchell's work also demonstrates the importance of taking theoretical physics seriously. He wasn't content to merely describe what was observed. He wanted to understand what the laws of physics implied about the universe, even if those implications seem strange or counterintuitive. This willingness to follow the mathematics wherever it leads, even into seemingly absurd territory, would become essential to understanding black holes in the 20th century. Without this approach, we might never have predicted black holes before observing them. What makes Mitchell's insight particularly impressive is that he arrived at it through pure reasoning, without any observational evidence to guide him. He was essentially asking a hypothetical question. What would happen if we pushed Newton's laws to their logical extreme? This kind of thought experiment would become a hallmark of theoretical physics in later centuries, but in Mitchell's time it was quite unusual to speculate so far beyond what could be directly observed. The very fact that he published these ideas in the Royal Society's journal shows how seriously his contemporaries took his theoretical work, even though there was no way to test his predictions at the time. This was a revolutionary idea for the time. The notion that there could be celestial bodies invisible to us, not because they were too faint or too far away, but because their gravity was strong enough to trap light itself, was completely novel. It suggested that the universe might contain hidden objects, dark masses that influence their surroundings, but remained forever unseen. Here's how Mitchell's argument worked, and it's quite clever given the tools he had available. If light is truly made of particles, as Newton had suggested, then to fly away from the surface of something such as the Earth or our Sun, each particle of light has to have been given some amount of kinetic energy, energy of motion. If the particle attempts to climb up and out of a gravitational field with less energy than what is needed to escape completely from that field, then that particle must inevitably fall back down to the surface, just like a ball thrown upward falls back to Earth. Think about throwing a ball upward. If you throw it gently, it rises a short distance and then falls back. Throw it harder and it goes higher before returning. There's a specific speed, called escape velocity, at which the ball would never return, escaping Earth's gravity entirely. For Earth, that speed is about 11 kilometers per second. Mitchell applied this same reasoning to light particles leaving the surface of a massive star. Since the Sun is the massive center of our solar system, containing almost all the mass of the entire system, it's quite heavy and creates a strong gravitational pull on everything around it. Clearly, corpuscles of light, these particles of light, somehow have enough energy to accomplish that escape today, and they did in 1783 as well, departing from the surface of the Sun without any difficulty whatsoever. We see the Sun shining, after all. The actual gravitational force acting on a particle flying away from the surface depends on both the total mass and the physical size contained under that surface, the radius of the object. Mitchell asked a fascinating question that no one had really considered before. What would the mass of the Sun have to be, or how large would it have to become, such that its escape speed would actually exceed the speed of light itself? At what point would even light particles be unable to escape? In 1783, scientists already had a pretty good idea about what the speed of light was, thanks to measurements by Ole Rømer and others who had studied the timing of Jupiter's moons. And with Mitchell's numbers and calculations, if you kept the Sun's density exactly the same as it currently is, but made the Sun 500 times physically larger in diameter, then light itself could not exit from the Sun's surface. the gravity would be too strong. In Mitchell's own words from the paper, all light emitted from such a body would be made to return to it by its own proper gravity. The light would be pulled back, unable to reach any distant observer. Thus, Mitchell termed such theoretical objects dark stars, stars that produced light, perhaps, but whose light could never reach us. For those playing along at home with better modern numbers for the sun's mass and size and the speed of light, it works out to be about 150 times the current solar diameter, or roughly 70% of an astronomical unit. That's quite a large theoretical object, almost as wide as the distance from the Sun to Venus. In 1796, working independently of Mitchell on the other side of the English Channel, Pierre-Simon de Laplace, one of the most famous mathematicians of the 18th century, and indeed in all of history, discovered that there really could be stars whose gravitational field could be strong enough that the escape speed would equal or exceed the speed of light. Where Mitchell's arguments were mostly philosophical in nature and based on thought experiments, Laplace developed his line of reasoning with rigorous mathematical precision and careful calculation. He included this idea in his book Exposition du Système du Monde. Laplace was an extraordinary mathematician who made fundamental contributions to celestial mechanics, probability theory, and many other fields. His work on the stability of the solar system was groundbreaking. He was also one of the first to propose the nebula hypothesis for the formation of the solar system, an idea that has largely been confirmed by modern observations. The wave theory of light seemed to make dark stars impossible. If light was a wave propagating through space, it didn't make sense to talk about it being pulled back by gravity like a thrown ball. Waves weren't particles that could fall. This seemed to invalidate the entire concept. And for most of the 19th century, the idea of dark stars faded from scientific discussion. Scientists moved on to other topics, and Mitchell and Laplace's speculation was largely forgotten except as a historical curiosity. There is some historical debate about whether or not Laplace knew of Mitchell's earlier arguments. Given the political troubles and limited communication between France and England at that particular tumultuous time in history, when the French Revolution was underway and tensions were high. Even still, Newton's revolutionary conception on how gravity operates, his inverse square law, and his mathematical description of gravitational attraction really did create a ripe new world, ready for scientific learning and exploration. The idea that gravity could be so strong as to trap even light was a natural, if startling, consequence of taking Newton's ideas seriously. What made Einstein's theory even more remarkable was that it made specific, testable predictions that differed from Newton's theory. Light from distant stars should be bent by the sun's gravity during a solar eclipse, something that was dramatically confirmed by Arthur Eddington's expedition in 1919. The orbit of Mercury should precess or shift slightly in a specific way that Newton's theory couldn't explain, and Einstein's theory predicted this precisely. Time itself should run slower in stronger gravitational fields, an effect we now have to account for in GPS satellites. All of these predictions were eventually confirmed by observation, vindicating Einstein's geometric view of gravity and establishing general relativity as our best description of gravity. To understand how revolutionary this was, imagine you're trying to walk in a straight line across a surface, but the surface itself is curved, like the surface of a sphere. You'll naturally follow a curved path, even though you're walking straight from your own perspective. Einstein realized that massive objects curve the four-dimensional fabric of space-time in much the same way, and everything moving through that space-time, including light, follows the curves. This was a complete paradigm shift from the Newtonian view of gravity as an attractive force reaching across space. But the idea of dark stars didn't really go anywhere for a long time. It remained a curiosity, an interesting theoretical possibility that most scientists didn't take seriously. Part of the problem was that Newton's theory, as successful as it was, didn't really predict when or how such objects might form in nature. It remained a mathematical curiosity without any clear physical realization. It took until Einstein's remarkable reformulation of gravity into a geometrical construct, into his general theory of relativity, before any major advancements could occur in this field of study. Einstein showed that gravity wasn't a force in the traditional sense, but rather a curvature of space-time itself. This was a radical reimagining of gravity. Instead of thinking of massive objects pulling on each other across empty space, Einstein proposed that massive objects curved the fabric of space-time around them, and other objects simply follow the straightest possible paths through that curved space-time. A planet orbiting the Sun isn't being pulled by an invisible force. It's following a curved path through space-time that has been warped by the Sun's mass. Karl Schwarzschild, a German physicist and astronomer, produced the first exact solution to the Einstein field equations of general relativity, equations that describe this new understanding of gravity. He set them down carefully in a letter to Einstein on the 22nd of December in 1915, just weeks after Einstein had published his theory. He wrote this important work while serving in World War I, stationed on the dangerous Russian front, calculating solutions to Einstein's equations in between artillery barrages. The fact that Schwarzschild could produce this exact solution so quickly, under such difficult circumstances, speaks to both his brilliance and his dedication to understanding the universe. Many physicists had struggled with Einstein's complex equations, which were notoriously difficult to solve. Schwarzschild found a way to simplify them for a specific case, a spherically symmetric mass distribution, and discovered an exact solution. Schwarzschild concluded the letter by writing something quite poignant and touching. As you can see, the war has treated me kindly enough, in spite of the heavy gunfire all around, to allow me to get away from it all and take this walk in the land of your ideas. It's a beautiful statement about the power of science and mathematics to transport us beyond our immediate circumstances. The field equations at the top of his work described the profound relationship between the curvature of space-time on one side and the matter and energy embedded in that space-time on the other. His solution, now known as the Schwarzschild solution, was specifically for space-time surrounding a static, non-rotating, spherically symmetric matter distribution, with nothing else in the universe to complicate matters. It was the simplest possible case, but it was exact. We'll look at this particular solution in greater detail a bit later. In 1916, Einstein wrote back to Schwarzschild about this remarkable result, clearly impressed. "I have read your paper with the utmost interest, and I had not expected that one could formulate the exact solution of the problem in such a simple and elegant way. I liked very much your mathematical treatment of the subject, and next Thursday I shall present the work to the Academy with a few words of explanation." Sadly and tragically, Schwarzschild died the very next year, in 1917, of a painful genetic disease that developed while he was serving in the German army. He was only 42 years old. Who knows what other remarkable contributions he could have made to physics, to mathematics, to astronomy, had he been able to live a much longer and more productive life. His name lives on, though, attached forever to the radius that defines the boundary of a black hole. For many years after Schwarzschild's work, physicists debated whether the mathematical singularity in his solution was physically real or merely an artifact of the coordinate system he used. Some argued that the singularity would never actually form in nature, that some physical process would prevent complete collapse. It took decades to fully understand that the singularity was indeed real and unavoidable under certain conditions. Then, jumping ahead about 20 years to 1939, Robert Oppenheimer, who would later become famous as the scientific director of the Manhattan Project, and his graduate student Hartland Snyder, described what would happen to a star that had exhausted all possible forms of nuclear fusion in its core and exceeded the critical limit of neutron degeneracy pressure, the quantum mechanical pressure that supports neutron stars. With absolutely nothing left to hold it up against gravity's relentless and unyielding pull, it would collapse down catastrophically to an infinite singularity, a black hole. And it is actually this important paper, this 1939 publication, where the term black hole truly originates in the scientific literature. Well, actually, they didn't use that exact term yet. The phrase black hole as we know it today was popularized much later in the 1960s by the physicist John Archibald Wheeler. But the concept, the idea of complete gravitational collapse to a singularity that was Oppenheimer and Snyder, Wheeler, incidentally, was a remarkable communicator of science and coined several other memorable phrases, including wormhole and quantum foam. He had a gift for making complex ideas accessible and memorable. The term black hole perfectly captured the nature of these objects, dark, mysterious, and inescapable. Oppenheimer himself, just earlier that same year, 1939, along with a couple of other colleagues, had figured out how neutron degeneracy pressure, a quantum mechanical effect, could support an ultra-massive, ultra-compact object which he termed a neutron star. These would be objects left behind after supernova explosions, incredibly dense balls of neutrons. Oppenheimer and Snyder then wondered what would happen if even that tremendous pressure broke down completely, if the star was too massive even for neutron degeneracy to support. They concluded, through their calculations, that absolutely nothing in the known laws of physics could support the mass of the compact object at that point. They found that this object would freefall catastrophically all the way down to a mathematical singularity, with nothing left in existence below it or inside it. It would be a true singularity, a point of infinite density, zero volume, where the laws of physics as we understand them would break down entirely. Let's look a bit closer at Oppenheimer and Snyder's careful reasoning, starting with the known properties of white dwarfs, which were already understood at that time. White dwarfs are extraordinarily dense objects, stellar remnants left behind when stars like our Sun exhaust their nuclear fuel. They possess a mass approximately equivalent to that of our Sun, all that material compressed down. But the volume of a typical white dwarf is comparable to that of the Earth. Imagine squeezing the entire mass of the Sun into a ball the size of our planet. The gravitational stability of a white dwarf, what keeps it from collapsing further under its own weight, is maintained through the unusual pressure of what's called degenerate electron gas, rather than through the more familiar gaseous pressure states we encounter in everyday life with normal gases, and certainly not a liquid or solid state in any conventional sense of those words. The gaseous nature of white dwarfs is more akin to a solid, but only in a colloquial sort of way when we think about their rigidity and incompressibility. A degenerate electron gas is characterized by the electrons occupying the lowest possible energy states available to them, all crammed together. This is a quantum mechanical effect. The Pauli exclusion principle says that no two electrons can occupy exactly the same quantum state. So once the lower energy states are filled, electrons are forced into higher energy states, creating an outward pressure that resists further compression. This quantum pressure is completely different from the thermal pressure in normal gases. In a normal gas, pressure comes from the random motion of particles colliding with each other and with container walls. The faster the particles move, the higher the temperature and pressure. But in a degenerate gas, the pressure arises from the quantum mechanical constraint that fermions cannot occupy the same state regardless of temperature. A white dwarf could be completely cold at absolute zero, and the degeneracy pressure would still be there. This prevents any further compression of the gas, even if there is some large addition of mass to the star, which might seem counterintuitive. As we saw in my earlier video on white dwarfs, the odd thing about a degenerate gas is that if additional mass is introduced into a white dwarf, its physical size will actually decrease, not increase. In other words, its radius shrinks the more massive it becomes. The added mass compresses the star more, forcing the electrons into even higher energy states. This is completely counterintuitive to our everyday experience, where adding more matter usually makes things bigger. Because of this strange inverse relationship between mass and radius, there is a maximum possible mass for white dwarfs. Add too much mass, and the whole structure becomes unstable. The maximum mass threshold for a degenerate electron gas to support is 1.44 solar masses. This critical value is known as the Chandrasekhar limit, named after the brilliant astrophysicist Subrahmanyan Chandrasekhar, who calculated it in the 1930s while still a young man in his 20s. Chandrasekhar's work on this limit was initially met with skepticism by some established astronomers, particularly Arthur Eddington, who refused to believe that stars could collapse catastrophically. The debate became quite heated at times, but Chandrasekhar's mathematics was impeccable, and eventually the physics community accepted his result. He was awarded the Nobel Prize in Physics in 1983, in part for this work. It comes about because as the allowed position and momentum states for the electrons get filled up one by one, the only available momentum states remaining for additional electrons are those with speeds rapidly approaching the speed of light. Since no physical object can travel faster than light, or even precisely at the speed of light, according to the theory of relativity, this fundamental speed limit of the universe gives a firm upper boundary to the allowed mass of white dwarfs. The implications of this limit are quite profound because they dictate all the possible evolutionary pathways of all stellar remnants throughout the universe. What happens to a star after it dies depends crucially on whether its remnant core exceeds this limit or not. The Chandrasekhar limit is not something that is easily breached under normal circumstances. A star has to be quite massive to leave behind a core that exceeds this limit. However, if the conditions are exactly right, electron degeneracy pressure can be bypassed and superseded by another form of quantum pressure, another way for nature to resist gravitational collapse. Much more massive stars than our Sun, stars with perhaps 10 or 20 or more times the Sun's mass, are capable of producing what we call a Type II supernova, a catastrophic explosion at the end of the star's life. If such a star has, say, a pre-supernova mass exceeding approximately 18 solar masses, it would result in a violent supernova explosion with a core mass larger than about 2.5 or 3 solar masses remaining behind after the explosion blows away the outer layers. In such dramatic instances, electron degeneracy pressure is completely overwhelmed and bypassed by gravitational forces. These massive star explosions are among the most energetic events in the universe. For a brief period, a supernova can outshine an entire galaxy containing hundreds of billions of stars. The energy released is almost incomprehensible, equivalent to the total energy output of the Sun over its entire 10 billion year lifetime, all released in a matter of seconds or hours. When the core of such a massive star collapses during the supernova, the electrons are forced to combine with protons through a process called electron capture, creating neutrons and releasing ghostly particles called neutrinos. The neutrinos carry away tremendous energy. This process leads to the formation of what we call neutron degeneracy pressure. In this extreme state, it's not the electrons providing the outward push against gravity anymore, but rather the neutrons themselves, packed together at incredibly and almost incomprehensibly high densities. Just like electrons, neutrons are fermions. They obey the same Pauli exclusion principle. This means that no two neutrons can occupy the same quantum state simultaneously. As neutrons get packed closer and closer together, they're forced into higher and higher energy states, creating a powerful outward pressure that can, at least temporarily, resist further collapse. The result is what we call a neutron star, an object with a mass between about 1 and 3 solar masses, but compressed into a sphere with a radius of only about 10 to 15 kilometers. That's roughly the size of a small city, yet containing more mass than our entire sun. Think about that for a moment. All the mass of the sun compressed into something the size of Manhattan. The density is almost incomprehensible to our everyday experience. A teaspoon of neutron star material, just a tiny amount, would weigh about 1 billion tons here on Earth. You couldn't even lift it with the strongest crane ever built. The surface gravity is so intense that the escape velocity approaches a significant fraction of the speed of light, perhaps 20 to 40% of light speed. If you could somehow stand on the surface of a neutron star, which you couldn't because you'd be instantly flattened, you'd weigh about 100 billion times more than you do on Earth. The gravity would be so strong that mountains on a neutron star can be only millimeters tall before the gravity smooths them out. The surface is thought to be incredibly smooth, smoother than a billiard ball. However, even neutron degeneracy pressure has its limits. Physics imposes boundaries on everything. There exists a maximum mass that neutron degeneracy pressure can support, similar to the Chandrasekhar limit for white dwarfs, but at a higher mass. This limit is called the Tolman-Oppenheimer-Volkoff limit, typically abbreviated as the TOV limit. The exact value of this limit is still somewhat uncertain and is an active area of research because it depends on the poorly understood behavior of matter at extremely high densities we cannot reproduce in any laboratory on Earth or anywhere else we can access. Current estimates based on theoretical models and observational constraints place this limit somewhere between about 2 and 3 solar masses, though the exact number remains an active area of research and debate among physicists. Different theoretical models of the equation of state of ultra-dense matter give slightly different values. When a stellar core exceeds the TOV limit, when it's too massive for even neutron degeneracy pressure to support, then neutron degeneracy pressure fails completely. There is simply nothing left in our understanding of physics that can prevent further collapse. No known force or pressure, quantum mechanical or otherwise, can counteract the overwhelming pull of gravity at this point. The core continues to collapse, shrinking smaller and smaller, denser and denser, without any way to stop. It continues to shrink until it forms what we call a singularity. At this singularity, density becomes infinite. Space becomes infinitely curved. Our equations break down completely. The laws of physics, as we understand them, no longer apply, or at least we don't know how to describe what happens there. This is how stellar mass black holes are born in the universe, from the deaths of the most massive stars in nature. But not all black holes form this way. There are other types and other formation mechanisms we'll explore as we continue. Before we dive deeper into the nature and properties of black holes themselves, let's take a moment to understand what happens during this final collapse from a slightly different perspective, one that reveals just how strange these objects truly are. Imagine you're an outside observer, perhaps on a spacecraft at a safe distance, watching a massive star's core collapse into a black hole. You're watching this catastrophic event unfold through your telescope. As the core shrinks smaller and smaller, something strange begins to happen to time itself around the collapsing object. According to general relativity, Einstein's theory of gravity, intense gravitational fields cause time to slow down relative to regions of weaker gravity, far away from strong gravitational sources. This effect is called gravitational time dilation, and it's been measured and confirmed in numerous experiments here on Earth and in space. We actually use corrections for gravitational time dilation in the global positioning system. GPS satellites orbit high above Earth, where gravity is slightly weaker than at the surface. Time runs slightly faster up there, about 45 microseconds per day faster. If we didn't correct for this effect, GPS coordinates would drift by kilometers every day. The fact that GPS works so precisely is a testament to the accuracy of Einstein's predictions. As the collapsing core approaches what will become the event horizon, the boundary of the black hole, the surface appears to slow down from your perspective as an outside observer watching from far away. The light from the collapsing surface becomes increasingly redshifted, shifting toward longer, redder wavelengths as the photons struggle to climb out of the deepening gravitational well, losing energy in the process. Wheeler's contributions went far beyond just naming. He trained a generation of physicists who would go on to make fundamental contributions to black hole physics, including Kip Thorne, who would later win the Nobel Prize for his work on gravitational waves, and many others who shaped the field. Wheeler had an extraordinary ability to ask deep questions that got to the heart of physical phenomena. He helped transform black holes from mathematical curiosities into serious objects of astrophysical study. Under his guidance and inspiration, black holes went from being regarded as strange theoretical predictions that probably didn't exist in nature to being recognized as real, detectable objects that play crucial roles in the cosmos. He reportedly first used the term publicly in a lecture in 1967, though the exact circumstances are debated by historians. According to some accounts, an audience member suggested it during a Q&A session. Regardless of its precise origin, the name caught on immediately. It perfectly captured the essence of these objects. They're black because they emit no light, and they're holes in space-time itself, regions where the normal structure of space and time breaks down. The term was so evocative and appropriate that within a few years, almost everyone in physics had adopted it. John Archibald Wheeler deserves special mention for his role in bringing black holes into the mainstream of physics. Before Wheeler popularized the term black hole in the 1960s, these objects were called various things: frozen stars, collapsed stars, or simply gravitationally completely collapsed objects, which was quite a mouthful. Different physicists used different terminology, which made it harder for the field to develop a unified understanding. Wheeler recognized that a catchy, memorable name would help focus attention on these bizarre objects. From your vantage point, far away from the action, the collapse appears to take an infinite amount of time to actually cross the event horizon. The surface seems to freeze at the horizon, slowing down asymptotically, never quite reaching it in your frame of reference. The light becomes so redshifted that it fades from view entirely. The photons stretch to longer and longer wavelengths until they become undetectable. The star doesn't appear to disappear suddenly in a flash. Rather, it fades gradually into darkness over time, becoming invisible against the black backdrop of space, leaving behind only its gravitational influence. But here's where it gets truly interesting and mind-bending. If you were somehow riding along with the collapsing matter itself, falling inward with the doomed core, your experience would be completely and radically different from the outside observer. From your perspective, falling toward what will become the singularity at the center, you would cross the event horizon in a finite amount of your own time, your proper time. You wouldn't notice anything particularly special about the exact moment you crossed it, at least not for a stellar mass black hole where the horizon might be relatively small. There would be no wall, no physical barrier, no sensation of passing through anything unusual or tangible, no sign saying now entering black hole. You would simply continue falling inward, drawn inexorably toward the singularity at the center by the overwhelming force of gravity. You wouldn't feel yourself slowing down or freezing. From your perspective, everything would seem normal, at least until the tidal forces became too strong. This profound difference in perspectives between the outside observer who never sees you cross and you yourself who crosses in finite time is one of the most fascinating and counterintuitive aspects of black holes. It demonstrates how profoundly gravity can warp not just space, but time itself, and how different observers can have radically different but equally valid perspectives on the same events. The event horizon represents a boundary in space-time, a point of no return, beyond which events cannot affect an outside observer in any way. Once something crosses this boundary, it is forever cut off from the rest of the universe, causally disconnected. No signal, no information, not even light itself can escape to tell us what happens inside. Let's now turn our attention to understanding the structure and properties of black holes themselves in more detail, to really get into what these objects are. The simplest type of black hole that we can describe mathematically is given by the Schwarzschild solution we mentioned earlier, the one Karl Schwarzschild discovered in 1915. This solution applies to a non-rotating, electrically neutral black hole sitting alone in otherwise empty space. It's the most basic case. It's characterized by just one single number, its mass. Everything about this black hole is determined by how massive it is. The key defining feature of a Schwarzschild black hole is the event horizon, located at what we call the Schwarzschild radius. This radius marks the boundary of the black hole, the point of no return. The Schwarzschild radius is directly proportional to the mass of the black hole. Double the mass, double the radius. The formula is quite simple. The radius equals 2 times the gravitational constant times the mass divided by the speed of light squared. For a black hole with the mass of our Sun, 1 solar mass, the Schwarzschild radius works out to be about 3 kilometers, just under 2 miles. That means if you could somehow compress the entire Sun down to a sphere with a radius of 3 kilometers, smaller than most towns, it would become a black hole. All that mass, all 99.8% of the mass of the solar system, compressed into a ball 6 kilometers across. For a black hole with 10 times the mass of the Sun, the Schwarzschild radius would be 30 kilometers, or about 19 miles across. For a million solar mass black hole, like smaller supermassive black holes, the radius extends to about 3 million kilometers, several times the diameter of the Sun. For M87's monster, the radius is about 120 astronomical units, larger than the orbit of Pluto. The event horizon is fundamentally a one-way surface in space-time. Anything and everything can fall in through it, but nothing, absolutely nothing, can come out from inside it. It's not a physical surface in the traditional sense that you could touch or stand on. There's no solid barrier there, no material shell, nothing you could build a structure on. It's simply a mathematical boundary in space-time, an abstract surface where the escape velocity equals the speed of light. Below this radius, inside this boundary, all possible paths through space-time lead inevitably inward toward the singularity at the center. There's no way out. Even a beam of light directed radially outward, straight up from just inside the event horizon, would be dragged inward, pulled back, unable to escape the grip of gravity. At the very center of the black hole, according to the mathematics of general relativity, lies the singularity. This is a point, or in some cases a ring, where the curvature of space-time becomes infinite and the density becomes infinite as well. All the mass of the black hole is concentrated at this single point of zero volume, or along a ring of zero thickness. At least, that's what the mathematics of general relativity tells us when we solve the equations. In reality, physicists believe strongly that our current theories break down at the singularity, that the equations are telling us they've reached their limits. We expect that a complete and consistent theory of quantum gravity, which we don't yet possess and are still working to develop, would resolve what really happens at this point, would smooth out the singularity somehow. The singularity represents a boundary of our knowledge, a place where our best theories fail. Now, real black holes in nature, the ones actually out there in space, are more complicated than the simple idealized Schwarzschild solution would suggest. Most black holes rotate, some of them very rapidly, spinning at tremendous speeds. A rotating black hole is described by a different, more complex solution to Einstein's equations, discovered by the mathematician Roy Kerr in 1963. The Kerr solution describes a rotating black hole, and it's characterized by two numbers instead of just one: the mass and the angular momentum, which tells us how fast it's spinning and in which direction. Kerr's discovery was a major breakthrough. For decades, physicists had searched for a solution that described a rotating black hole, but the mathematics proved extremely difficult. When Kerr finally found the solution, it opened up new understanding of how black holes could form and evolve in the real universe, where rotation is the norm rather than the exception. Rotation changes the structure of the black hole significantly. It's not just a simple sphere anymore. A rotating black hole has two horizons instead of just one. The outer horizon is still the event horizon, the point of no return, similar to the Schwarzschild case, but slightly different in radius. But there's also an inner horizon at a smaller radius inside the first one, called the Cauchy horizon. The structure is more complex, layered. Between these two horizons lies a region called the ergosphere, a zone unique to rotating black holes. In the ergosphere, space-time itself is dragged around the black hole in the direction of rotation, like water swirling around a drain. This effect is called frame dragging, or the Lense-Thering effect. Within the ergosphere, it's impossible to remain stationary relative to distant stars. Everything, even light, is forced to move in the direction of the black hole's rotation to some degree, dragged along by the rotating space-time itself. Though it's still possible to escape from the ergosphere if you're moving fast enough and in the right direction. Various approaches to quantum gravity have been proposed, including string theory, loop quantum gravity, and others, but none have been conclusively verified. What all these approaches suggest is that space-time itself probably has some kind of granular structure at extremely small scales, perhaps around the Planck length, which is about 10 to the minus 35 meters. At these scales, the smooth geometry of space-time, described by Einstein's equations, probably breaks down into something more complex. The singularity, with its infinite curvature and infinite density, is likely telling us that we've reached these quantum scales where our current understanding fails. The problem of the singularity points to one of the deepest unsolved problems in physics: how to merge quantum mechanics with general relativity into a single, consistent theory. General relativity works beautifully at large scales, describing planets, stars, and galaxies with incredible precision. quantum mechanics works beautifully at small scales, describing atoms, molecules, and subatomic particles with equal precision. But these two theories are mathematically incompatible in certain extreme situations, and the singularity at the center of a black hole is exactly such a situation. The ergosphere is particularly interesting because it's theoretically possible to extract energy from a rotating black hole through a process called the Penrose process, named after physicist Roger Penrose. A particle entering the ergosphere could split into two, with one piece falling into the black hole with negative energy and the other escaping with more energy than the original particle had. This would slow down the black hole's rotation while extracting energy. Some astrophysicists think this might be happening in real astrophysical systems. The singularity in a rotating black hole is also different from the point singularity in a non-rotating one. Instead of a point at the center, the mathematics predicts a ring singularity, a circular line of infinite density rotating in the equatorial plane. Again, we don't really know if this ring singularity is physically real or if quantum effects would change the picture at such small scales, smoothing it out into something else entirely. Black holes can also carry electric charge in principle, though in practice this is probably quite rare in nature. A charged black hole is described by the Reisner-Nordström solution, or if it's both charged and rotating, by the even more complex Kerr-Newman solution. These solutions involve additional horizons and more complex mathematical structures. However, most astrophysicists believe that real black holes in space quickly lose any significant charge through interactions with the surrounding plasma and gas. Electrically charged particles that would be attracted to or repelled by the black hole and would neutralize it. So we typically don't worry too much about highly charged black holes in practical astrophysics. There's a beautiful and elegant theorem in general relativity called the no-hair theorem, or sometimes the uniqueness theorem. This theorem states that black holes are remarkably simple objects in the end, despite their exotic nature. Once a black hole has formed and settled down into a stable state, relaxing after its formation, it's completely characterized by just three numbers: its mass, its angular momentum, and its electric charge. That's it, just three numbers. No other information about what fell in to make the black hole is preserved or accessible to outside observers. It doesn't matter if the black hole formed from the collapse of a massive star, or from the merger of two neutron stars, or from a cloud of gas in the early universe, or from a million smaller black holes colliding. Once it's formed and settled, all that history is erased. The black hole has no memory of its past, no distinguishing features or complexity beyond those three numbers. It's just mass, spin, and charge. In this sense, black holes are said to have no hair, meaning no additional distinguishing characteristics, no unique markings, no texture, no bumps or features. All black holes with the same mass, spin, and charge are completely identical and indistinguishable. This simplicity is both elegant and somewhat troubling. It means that a tremendous amount of information appears to be lost forever when matter falls into a black hole. This information loss problem is one of the deepest puzzles in theoretical physics, connecting general relativity to quantum mechanics in ways we don't yet fully understand, and raising questions about the fundamental laws of physics. Let's talk about what happens near a black hole from the perspective of an observer who's falling in, to make this more concrete and visceral. Imagine you're an astronaut approaching a stellar mass black hole in a spacecraft, perhaps one with 10 times the mass of the Sun. As you fall toward the event horizon feet first, drawn by gravity, you begin to notice something deeply disturbing happening to your body. The gravitational pull on your feet is stronger than the pull on your head because your feet are just a little bit closer to the black hole, a few feet or a couple meters closer. This difference in gravitational force across your body is called a tidal force, the same kind of force that causes tides on Earth from the moon's gravity, but much, much stronger here. For a stellar mass black hole, one just 10 times the Sun's mass, with a Schwarzschild radius of only 30 kilometers, these tidal forces become extremely strong well before you reach the event horizon. The difference in gravity between your head and your feet across just the 2-meter length of your body would be enormous. The effect would stretch you vertically like a piece of taffy being pulled, making you longer and thinner. At the same time, you'd be compressed from the sides, squeezed horizontally. This gruesome and painful process has been given the colourful and somewhat darkly humorous name of spaghettification. You'd be stretched into a long, thin strand, like a piece of spaghetti. The ergosphere opens up fascinating theoretical possibilities. In principle, you could use the Penrose process to extract energy from a rotating black hole's spin, gradually slowing it down over time. Some astrophysicists have speculated that advanced civilizations might one day use black holes as power sources this way, extracting energy until the black hole stops spinning. While this remains firmly in the realm of speculation, it shows how black holes are not just cosmic destroyers, but potentially useful objects in the far future. Every time a particle escapes with extra energy through the Penrose process, the black hole loses a tiny bit of its rotational energy, demonstrating that even these extreme objects must obey conservation laws. The frame dragging effect around rotating black holes, while predicted by theory, was incredibly difficult to observe directly for many years. In 2004, NASA's Gravity Probe B mission was specifically designed to measure frame dragging around Earth, which rotates much more slowly than a black hole, but is close enough to measure precisely. The mission took extraordinarily precise measurements over many years and confirmed that Earth's rotation does indeed drag space-time around with it, exactly as Einstein's equations predicted. This gave us confidence that our understanding of frame dragging around rapidly rotating black holes is correct. Long before you reach the event horizon, the tidal forces would be strong enough to tear your body apart at the molecular level, ripping molecules from each other, then at the atomic level, shredding atoms themselves, breaking you down into a stream of subatomic particles spiraling inward. It would not be a pleasant way to go, to say the least, though it would at least be quick. Interestingly, for a supermassive black hole, the story is quite different, almost the opposite. Because the event horizon is so much farther from the singularity, many thousands or millions of kilometers away, the tidal forces at the event horizon are actually quite gentle, barely noticeable. The gravitational field, while strong, changes slowly over distance near the horizon of a supermassive black hole. You could cross the event horizon of a billion solar mass black hole without experiencing any significant discomfort at all. You wouldn't feel anything unusual. You wouldn't notice the moment you crossed it. There would be no sensation, no sign. Of course, once inside, you'd still be doomed to reach the singularity eventually. And as you got closer and closer to it, the tidal forces would ultimately become infinite and deadly. But you might have many minutes or even hours of perfectly normal existence before that happened. You could float there, looking around, observing, for a while before the end. This is one of the strange paradoxes of black holes. The bigger they are, the gentler they are at their boundaries. Another strange effect you'd experience as you fell in would be related to time and the light around you. Looking back over your shoulder toward the outside universe, you'd see something bizarre. Time in the outside universe would appear to speed up dramatically from your perspective. Light from distant stars would become blue-shifted, compressed to shorter wavelengths and higher energies as you fell into the gravitational well. The entire future history of the universe outside would appear to unfold before your eyes in the brief time before you reached the singularity, compressed into moments. You might see stars being born and dying, galaxies colliding, all happening in fast forward. Stephen Hawking initially argued that information really is destroyed in black holes, that this was just something we had to accept. But this created a paradox. It meant that quantum mechanics and general relativity were fundamentally incompatible, that one of them had to be wrong. Other physicists, including Leonard Susskind and Gerard Hooft, argued strenuously that information must be preserved somehow, leading to heated debates that became known as the Black Hole Information War. These debates have driven much of the theoretical work on black holes in recent decades and have led to fascinating new ideas about the nature of space-time, including the holographic principle, which suggests that all the information in a three-dimensional region of space might be encoded on its two-dimensional boundary. The information loss problem is particularly troubling because it seems to violate one of the fundamental principles of quantum mechanics, that information about a quantum system is never truly destroyed, only transformed. In quantum mechanics, if you know the complete quantum state of a system at one time, you can in principle calculate what it was at any earlier time and what it will be at any later time. This reversibility is called unitarity, and it's been tested in countless experiments at the quantum scale. But black holes seem to violate this principle. When matter falls into a black hole, all information about its quantum state appears to be lost forever, erased from the universe. Meanwhile, looking ahead toward the singularity in front of you, you'd see all the light that has ever fallen into the black hole before you, all the photons from all the matter and radiation that preceded you, compressed and blue-shifted to enormous and potentially lethal energies, a wall of radiation. The view would be both spectacular and terrifying. From the outside, however, observers watching you would see something very different, as we mentioned before. They'd watch you approach the event horizon, moving slower and slower in their frame of reference. Your image becoming increasingly redshifted, shifting toward red and then infrared and then radio waves. Eventually, you'd appear to freeze at the horizon, your image fading exponentially as the light from your body became stretched to longer and longer wavelengths, becoming dimmer and dimmer. You'd effectively vanish from view, fade to black, but the outside universe would never actually see you cross the horizon in finite time. You'd asymptotically approach it forever from their perspective. This strange disconnect between different perspectives, this radical disagreement about what happens, is a profound consequence of the extreme warping of space-time near a black hole. Different observers, moving differently through space-time, experience reality differently. There's no single absolute truth about when you crossed, no universal now. This is one of the most mind-bending aspects of relativity. Now let's discuss the different types and categories of black holes we observe in the universe, categorized primarily by their mass, since mass is the most important property. Stellar mass black holes are the ones formed from the collapse of massive stars, as we described earlier. They typically have masses ranging from about 3 or 5 solar masses on the low end, up to perhaps 100 solar masses or so on the high end, though recent observations have found some even more massive than that. We've detected many dozens of these stellar mass black holes through various methods, which we'll discuss in more detail shortly. Then there are the supermassive black holes, absolute monsters that lurk at the centers of most, if not all, large galaxies throughout the universe. These behemoths have masses ranging from about 1 million solar masses on the small end, up to tens of billions of solar masses for the largest ones we've found. They're not just a little bigger than stellar mass black holes. They're millions or billions of times more massive The supermassive black hole at the center of our own Milky Way galaxy, called Sagittarius A star, has a mass of about 4 million times that of the Sun. That's 4 million solar masses concentrated in a relatively small region. The black hole at the center of the galaxy M87, which we'll talk about more later and which has been photographed, weighs in at about 6.5 billion solar masses. It's a true giant, one of the most massive black holes known. How did such enormous black holes form? This is still an active area of research, and we don't have all the answers yet. They couldn't have formed simply from the collapse of a single star, no matter how massive that star was. Stars just don't get that big. One possibility is that they grew from smaller seed black holes in the early universe, gradually accumulating mass by swallowing gas, dust, and stars over billions of years, feeding continuously. Another possibility is that they formed directly from the collapse of massive clouds of gas in the very early universe, perhaps in the first billion years after the Big Bang, before stars had even formed or shortly after the first stars appeared, or perhaps they grew primarily through mergers, with smaller black holes colliding and combining to form ever larger ones over cosmic time. Recent observations of very distant quasars, extremely luminous active galactic nuclei, have shown that supermassive black holes with billions of solar masses existed when the universe was less than 1 billion years old. This is a puzzle. How did they grow so large so quickly? There simply wasn't enough time for them to grow from stellar mass seeds through normal accretion. This suggests that either they started much larger, or they were able to accrete matter much faster than we thought possible, or both. There should also be intermediate mass black holes, filling in the gap with masses between about 100 and 1 million solar masses, bridging the range between stellar mass and supermassive black holes. These have been harder to find observationally, and we have only a handful of confirmed or candidate objects in this mass range so far. They seem to be rare, or at least well hidden. Understanding this intermediate mass range is important for understanding how supermassive black holes grew from stellar mass seeds to their current enormous sizes. Did they pass through this intermediate phase? The search for these medium-sized black holes is an ongoing and exciting area of research in astrophysics. There's also theoretical speculation about primordial black holes that might have formed in the very early universe, perhaps in the first second after the Big Bang, from density fluctuations in the hot, dense soup of matter and energy that filled the universe then. These could potentially have a wide range of masses, from very tiny, perhaps as small as a grain of sand or even smaller, up to stellar mass or even larger. If they exist in sufficient numbers, they could potentially account for some or all of the mysterious dark matter that makes up most of the matter in the universe, the missing mass that we can't see but can detect gravitationally. However, we haven't found direct evidence for primordial black holes yet, despite searches, and the search continues. At the molecular level, the tidal forces would eventually overcome even chemical bonds. The very molecules that make up your body would be pulled apart, separated into individual atoms, and at the most extreme limits, approaching the singularity itself, even atomic nuclei might be disrupted, torn into individual protons and neutrons. You would be reduced to a stream of subatomic particles spiraling inward toward the singularity, all organized structure destroyed by the overwhelming force of gravity. This is the ultimate fate of any matter that crosses the event horizon and cannot be avoided by any known physics. The process of spaghettification is not just a colourful metaphor, but a real and terrible physical phenomenon. As the tidal forces grow stronger, your body would first be stretched uncomfortably, then painfully, then beyond the elastic limits of human tissue. Your bones would begin to separate, pulled apart at the joints and eventually fractured lengthwise. Blood vessels would rupture, unable to maintain their integrity across the growing pressure differential. Eventually, even individual cells would be torn apart, their membranes unable to withstand the difference in gravitational force between one side and the other. So how do we actually find and detect black holes? After all, they're black and they don't emit any light of their own by definition, so they should be invisible against the darkness of space, right? Well, while it's true that black holes themselves don't emit light, at least not in classical general relativity, we can detect them through their effects on their surroundings, through how they influence matter and light nearby. There are several clever and powerful methods astronomers have developed to find and study these invisible objects. One of the most powerful and productive methods involves looking for black holes in binary systems, where the black hole has a companion star orbiting around it, bound together by gravity. If the companion star is close enough to the black hole, within a certain distance, the black hole's intense gravity can pull matter away from the star's outer layers, stripping gas from its surface through a process called Roche-Lobe overflow. This stolen material doesn't fall directly into the black hole in a straight line. Instead, because of angular momentum and conservation laws, it forms a swirling disk around the black hole called an accretion disk, spiraling gradually inward. As the matter spirals inward through the accretion disk, viscosity and friction and magnetic fields heat it to incredibly high temperatures, millions of degrees Kelvin or more. At these extreme temperatures, far hotter than any star's surface, the gas emits intense X-rays, high-energy photons. These X-rays can escape and travel through space to reach us, making the system bright in X-ray wavelengths even though the black hole itself is dark. The X-rays flicker and vary on timescales of milliseconds to seconds, much faster than any normal star could vary. This rapid variability is a signature of matter in the innermost regions of the accretion disk, very close to the event horizon, where orbital speeds approach the speed of light and time dilation effects become important. These X-ray binary systems are one of our best and most reliable tools for finding stellar mass black holes. We observe many such systems in our galaxy and beyond, scattered throughout the Milky Way, where we see periodic X-ray emission and can measure the orbital motion of the visible companion star using spectroscopy. By studying how the companion star moves, analyzing its velocity and orbital parameters, we can determine the mass of the invisible object it's orbiting using Kepler's laws and Newton's laws. If that mass exceeds about 3 solar masses, the maximum possible mass for a neutron star, according to our understanding of physics, we can be quite confident we're looking at a black hole rather than a neutron star or white dwarf. One famous example is Cygnus X1, an X-ray source in the constellation Cygnus the Swan. It consists of a blue supergiant star orbiting an invisible companion with a mass of about 15 solar masses, well above the theoretical limit for a neutron star. This was one of the first objects to be widely accepted as a strong black hole candidate, though initially in the 1970s there was considerable debate and skepticism. In fact, Stephen Hawking and Kip Thorne, two of the most famous physicists of the 20th century, made a famous scientific bet about whether Cygnus X1 really was a black hole. Hawking, somewhat perversely, bet against it being a black hole, figuring he'd win either way. Either he'd be right and win the bet, or black holes would exist and he'd lose the bet but his life's work would be vindicated. Hawking eventually conceded the bet in 1990, though by then most astronomers were already convinced by the evidence. Another powerful method for finding black holes, particularly supermassive ones at galactic centers, involves looking very carefully at the motion of stars and gas near the centers of galaxies. If there's a massive compact object at the center, concentrated in a small region, it will gravitationally influence the orbits of nearby objects. By carefully tracking the motion of individual stars over many years or decades, we can map out the gravitational field in the region and determine the mass and location of the central object causing those motions. The best example of this method comes from patient observations of the center of our own Milky Way galaxy over more than 2.5 decades. Over more than 25 years, astronomers have meticulously tracked the orbits of stars very close to the galactic center, a region known as Sagittarius A star, using powerful infrared telescopes to see through the dust that obscures the view in visible light. These observations revealed that the stars are orbiting an invisible object with a mass of about 4 million solar masses, all contained within a region smaller than the orbit of Mercury around the Sun, a truly tiny volume for such a large mass. There's simply no other plausible explanation for such a huge concentration of mass in such a small volume besides a supermassive black hole. One particular star, designated S2 or SO2 depending on the team observing it, has been especially valuable for these studies. It completes a full orbit around the central black hole in only about 16 years, a relatively short period astronomically speaking, and its elliptical orbit brings it very close to the black hole at its nearest approach, within about 17 light hours of the event horizon, moving at about 3% of the speed of light at periapsis. By precisely measuring the star's position and velocity throughout its orbit using adaptive optics and interferometry, astronomers have been able to test predictions of general relativity in the strong gravitational field near the black hole. The observations match Einstein's predictions beautifully, including effects like gravitational redshift and perihelion precession, relativistic beaming, and the Schwarzschild precession of the orbit. This collapse releases an enormous amount of gravitational potential energy. Much of this energy goes into the neutrinos produced during the collapse, which flood outward in all directions. But some of it drives a powerful shock wave that propagates outward through the star's outer layers, blowing them off into space in what we observe as a supernova explosion. The supernova can briefly outshine an entire galaxy, releasing more energy in a few weeks than the Sun will produce in its entire 10 billion year lifetime. Yet despite this tremendous explosion, the core continues to collapse inward, forming a black hole. The black hole itself doesn't explode or emit light. It simply appears at the center, a new dark object where a stellar core once was. The formation of stellar mass black holes is one of the most violent events in the universe. When a massive star exhausts its nuclear fuel, the core suddenly loses the pressure support that has been holding it up against gravity for millions of years. The core collapses catastrophically, falling inward at speeds approaching a significant fraction of the speed of light. In less than a second, a stellar core larger than Earth can collapse down to a point just a few kilometers across. Andrea Ghez at UCLA and Reinhard Genzel at the Max Planck Institute shared the 2020 Nobel Prize in Physics for this work, along with Roger Penrose for his theoretical work on black holes, proving that singularities form inevitably from gravitational collapse. Their decades of patient observation provided some of the most convincing and unambiguous evidence we have for the existence of supermassive black holes. It was a triumph of observational astronomy and technological innovation. A more recent and revolutionary method for detecting black holes involves gravitational waves, ripples in space-time itself. According to general relativity, accelerating massive objects create ripples in the fabric of space-time itself, disturbances that propagate outward at the speed of light. These ripples travel outward from their source, stretching and squeezing space as they pass through it. The effect is incredibly tiny though, which is why gravitational waves remained undetected for a full century after Einstein first predicted their existence in 1916. That all changed on September 14th, 2015, when the Laser Interferometer Gravitational Wave Observatory, known as LIGO for short, made the first direct detection of gravitational waves from space. The signal came from two black holes with masses of about 29 and 36 solar masses, spiraling into each other and merging violently into a single, larger black hole, about 1,300 million light-years away from Earth, over 1 billion light-years distant. The detection opened up an entirely new way of observing the universe, a new window onto cosmic phenomena. The LIGO detectors are truly marvels of modern engineering and physics. Each detector consists of two perpendicular arms, each 4 kilometers, or about 2.5 miles long, arranged in an L-shaped configuration. Laser beams travel down each arm and bounce back from mirrors suspended as pendulums to isolate them from seismic vibrations, and the two beams interfere with each other when they recombine. A passing gravitational wave stretches space along one arm while compressing it along the perpendicular arm, causing a tiny change in the arm lengths and thus in the interference pattern of the laser light. The changes LIGO can detect are astonishingly small, almost unbelievably so, about 1/10,000th the diameter of a proton, or about 10 to the minus 19th meters. That's like measuring the distance to the nearest star to an accuracy smaller than the width of a human hair. It's a remarkably sensitive instrument. Despite this incredible sensitivity, or perhaps because of it, LIGO has to contend with a huge amount of noise and interference from many sources like earthquakes thousands of miles away, ocean waves hundreds of miles away, logging trucks driving by on nearby roads, even quantum fluctuations in the laser light itself due to the Heisenberg uncertainty principle. Sophisticated data analysis techniques and algorithms are required to extract the faint signal of a real gravitational wave from all this background noise, using matched filtering and other techniques. The September 2015 detection was unmistakable though, a clear signal above the noise in both detectors. The signal, lasting only about 1/5 of a second from start to finish, matched the predicted pattern from two black holes spiraling together almost perfectly. As they orbit each other, they lose energy to gravitational waves, the waves carrying energy away from the system, causing them to spiral closer and closer together, accelerating. The orbital frequency increases, and so does the frequency of the gravitational waves they emit. This produces a characteristic chirp signal, rising in frequency and amplitude as the black holes orbit faster and faster and merge, like a sound rising in pitch and volume, ending in a ringdown as the merged black hole settles down. From this one brief signal, scientists could determine the masses of the two original black holes, their distance from Earth based on the amplitude of the signal, and even the mass and spin of the final merged black hole left behind. They could also test general relativity in the strong field regime where gravitational effects are most extreme, comparing the observed waveform to theoretical predictions. The observations matched Einstein's predictions with remarkable precision, confirming the theory in a completely new regime never before tested. 3 leaders of the LIGO collaboration, Rainer Weiss, Barry Barish, and Kip Thorne, were awarded the 2017 Nobel Prize in Physics for this detection. Several theories have been proposed to explain this rapid growth. One idea is that supermassive black holes might not have started from stellar mass seeds at all, but from much more massive seeds formed directly in the early universe through the collapse of enormous gas clouds. Another possibility is that the early universe had physical conditions that allowed black holes to accrete faster than the Eddington limit would normally allow, perhaps because the gas was unusually dense or because magnetic fields channeled matter inward more efficiently. Understanding this growth process is crucial not just for understanding black holes, but for understanding how galaxies themselves formed and evolved, since supermassive black holes and galaxies seem to grow together in a connected way. How supermassive black holes grew so large, so quickly in the early universe remains one of the major unsolved problems in astrophysics. The most distant quasars we observe, powered by supermassive black holes, appear when the universe was less than 1 billion years old, less than 10% of its current age. For a black hole to grow from stellar mass, perhaps tens of solar masses, to billions of solar masses in less than 1 billion years, requires almost continuous feeding at extremely high rates. The black hole would need to be accreting matter at close to the theoretical maximum rate, called the Eddington limit, for essentially its entire existence. Since that first historic detection in 2015, LIGO and its European counterpart Virgo, and later also KAGRA in Japan, have detected dozens and dozens of black hole mergers, as well as mergers of neutron stars and mixed mergers between black holes and neutron stars. Each detection teaches us something new about these extreme objects, about how common they are, about their mass distribution, how they formed, and about the nature of gravity itself in these extreme conditions. The gravitational wave observations have confirmed that stellar mass black holes exist across the mass range predicted by stellar evolution theory. And they've revealed that black hole mergers are surprisingly common cosmic events, happening somewhere in the universe, perhaps once every few minutes. So these observations, along with the hundreds of confirmed gravitational wave events detected since that first groundbreaking one in 2015, provide some of the best and most direct evidence that we have for the existence of black holes. The detections are unambiguous and repeatable. The data is analysed carefully by multiple independent groups, and the results match theoretical predictions beautifully. It's very hard to explain these observations without invoking black holes. But in this day and age, there are a lot of people whose mantra is pictures or "it didn't happen, show me a photograph." All the gravitational wave events are real signals in the distortion of space-time itself, measured with extraordinary precision and confirmed by multiple detectors. But they are not pictures or images. They don't give us a visual photograph of what a black hole looks like. So the question naturally arises, are there actual images of black holes? Can we take a picture of one, a real photograph? Yes. Actually, we can look for black holes where their effects are visually evident, where we can photograph the light around them. Many galaxies in the universe are what are known as active galaxies. These galaxies have extremely bright cores whose luminosities can exceed the combined light from all the billions of normal stars in the rest of the galactic disk, or halo, outshining the entire rest of the galaxy. They also may have enormous jets of matter and energy that extend outward to millions of light years from the core, particularly in the most energetic varieties known as radio galaxies and quasars. Looking specifically at the galaxy designated Messier 87, or M87 for short, in the constellation Virgo, located about 53 million light-years away from Earth, we see a supergiant elliptical galaxy, one of the largest galaxies we know of. It has an extraordinarily bright core and a clearly visible jet extending about 5,000 light-years out from the centre into space. This jet has a distinct structure that can be observed in both radio wavelengths and visible light wavelengths. At the highest magnifications achievable in the radio wavelengths with the Very Long Baseline Array, or VLBA, bright knots or features in the jets can be observed to change from year to year, moving outward on size scales of about 1/10 of a light year. The material in the jet is travelling at about 85% of the speed of light, moving at what we call relativistic speeds, close enough to light speed that special relativistic effects become important. The total energy contained in the jet is about 10 to the 13th power times that of the total luminosity of all the stars in the entire Milky Way galaxy combined. That's an absolutely astounding and mind-boggling amount of energy, almost unimaginable. This incredible energy that propels this jet is coming from a volume that cannot be bigger than a few light years across, at most possibly much smaller. To put that in perspective and make it more concrete, in the Milky Way galaxy, the typical distance between neighbouring stars is about 3 light years or so. So we're talking about something creating 10 to the 23rd solar luminosities worth of power, more power than 10 trillion galaxies like the Milky Way, in a volume smaller than the distance between our Sun and the nearest star, Alpha Centauri. How is this even remotely possible? What could possibly generate such tremendous power in such a relatively small region of space? The only answer that makes sense, the only explanation that works, is a supermassive black hole, one of the largest in the known universe, actively feeding on surrounding matter. The Event Horizon Telescope collaboration, an international team of scientists, was specifically formed to directly image that black hole at the centre of M87. M87 is near enough to us that its black hole appears relatively large, in angular size on the sky, about 40 micro-arc-seconds across, and positioned favourably near the ecliptic plane, making observations easier with telescopes spread across the globe. So a coordinated worldwide observation campaign was organised to use radio telescopes operating in the sub-millimetre microwave region of the electromagnetic spectrum, wavelengths around 1.3 millimetres. Each participating telescope was outfitted with an extraordinarily accurate atomic clock to precisely timestamp the data, accurate to within a few picoseconds, and all observed the galaxy at roughly the same time during their observation windows in April 2017. The signals from all these different telescopes scattered around the globe could then be combined interferometrically, essentially turning the entire Earth into a single telescope with an effective diameter the size of our planet, about 13,000 kilometers. This technique, called Very Long Baseline Interferometry, or VLBI, allows for incredible angular resolution, far better than any single telescope could achieve on its own. The resolution was enough to read a newspaper in New York while standing in Paris, metaphorically speaking, or to see a donut on the moon from Earth. The huge amount of data collected during the observation campaign was stored on physical hard drives, hundreds of them. Because of the enormous distances between the participating telescopes scattered around the world, from Chile to Hawaii to Spain to the South Pole, transferring the multiple petabytes of data to a central processing location would literally take years using standard internet connectivity, even high-speed connections. The data rate was simply too high. So the collaborators packed the hard drives carefully into suitcases as carry-on luggage on commercial airplanes and physically flew copies to both Germany at the Max Planck Institute and Massachusetts at MIT for processing and analysis. It was faster and more reliable to fly the data across the ocean than to transmit it electronically. On April 10th, 2019, the Event Horizon Telescope collaboration held simultaneous press conferences around the world in multiple cities, including Brussels, Washington, Tokyo, and Santiago, to announce the first ever direct image of a black hole, a historic moment in astronomy. The image showed the central region of M87, spanning only about 13 thousandths of a light year across, a tiny fraction of a light year. What we're looking at in this historic and unprecedented image is the rotating disk of ionized gas, a glowing plasma, with a maximum diameter of about 25,000 astronomical units. Though much of that disk is well outside the field of this particular view, too faint to see. In the image, we only see the brightest regions of material around the black hole, the hottest and most intense parts. The size of the inner shadow of the black hole visible in the image is about 4 times the width of Pluto's entire orbit around the Sun. And if the Sun were positioned at the center of this image, the Voyager 1 space probe, the most distant human-made object currently traveling through interstellar space at about 17 kilometers per second, would be just reaching the glowing region at the edge of the dark center, the bright ring. The Event Horizon Telescope team was able to measure the black hole's mass quite precisely from the image and the motion of material in the accretion disk, determining it to be 6.5 billion solar masses. With an uncertainty of only about 10%, this enormous mass would have a Schwarzschild radius of about 120 astronomical units, about 4 times the distance from the Sun to Neptune. The shadow you see in the center of the image is about 500 astronomical units across in diameter. So the actual event horizon itself is about 2.5 times smaller in radius than the shadow that it casts on the surrounding light, about a factor of 2.5. The reason for this difference in size, why the shadow is larger than the event horizon, is the gravitational lensing effect we've talked about earlier in other contexts. The intense gravity of the black hole bends the paths of light rays passing near it, curving space-time around the black hole. Light from the accretion disk behind the black hole gets bent around the black hole, its path curved by gravity, creating a larger apparent shadow than the event horizon itself would create. Some of the light we see in the bright ring actually comes from the far side of the accretion disk, material on the opposite side of the black hole from us, its light bent around the black hole by gravity to reach us. We're seeing around the black hole, in a sense, seeing both the near side and the far side simultaneously. In 2023, the Event Horizon Telescope data were reconstructed and reanalyzed using an improved interferometric algorithm called PRIMO, which stands for Principal Component Interferometric Modeling, designed to enhance the resolution and clarity of the image even further using machine learning techniques. Again, the shadow of the black hole is shown to be about 2.5 times bigger in radius than the actual event horizon itself. The refined image closely resembles the computer-generated images that Kip Thorne and his collaborators and visual effects team created for the science fiction movie Interstellar, which came out in 2014. But that was Hollywood special effects, carefully calculated using Einstein's equations and ray tracing algorithms to be scientifically accurate for the film. This Event Horizon Telescope image is reality itself, actual light from actual photons that travelled 53 million light-years through space to reach us. The Event Horizon Telescope group has subsequently also successfully imaged Sagittarius A star, the supermassive black hole at the centre of our own Milky Way galaxy, releasing that image in May of 2022. This was actually more challenging than imaging M87's black hole. Despite Sagittarius A star being much closer to us, only about 26,000 light-years away versus 53 million for M87. The reason is that M87's black hole is so massive that the material in its accretion disk takes days or weeks to orbit around, moving relatively slowly. During an observation run of several hours or days, the structure remains relatively stable, changing slowly like a long exposure photograph of a still scene. Sagittarius A star, being about 1,000 times less massive, has material orbiting in just minutes, whipping around rapidly, so the structure changes rapidly during observation, blurring and shifting, like trying to photograph a squirming child or a fast-moving object with a long exposure. The structure was smeared out by the motion, making the imaging more difficult and requiring new analysis techniques to account for the variability. In both cases, though, we see the expected glowing accretion disk around the black hole, with light being gravitationally lensed around it, bending around the event horizon, creating that distinctive ring appearance with a dark center. We also see very clearly the dramatic size difference between these two cosmic behemoths. Our home galaxy's supermassive black hole, Sagittarius A star, is about 1,000 times less massive than M87's, and therefore about 1,000 times smaller in diameter, making for a very different appearance and challenge. This accretion disk of swirling material and the intense magnetic fields generated by the swirling and rotating in falling matter are understood to be the source of the relativistic jets emanating from M87's core and from other active galactic nuclei throughout the universe. The magnetic fields can become twisted and amplified by the rotating plasma in the disk through a dynamo process, much like the Earth's magnetic field is generated but far more powerful. These fields can then channel some of the infalling matter, redirecting it into narrow beams perpendicular to the disk, accelerating it to nearly the speed of light through processes we're still working to understand fully, involving magnetic reconnection and particle acceleration, and launching it outward as powerful jets that can extend for millions of light years, punching through the surrounding intergalactic medium. Since the first detection in 2015, LIGO and its European counterpart Virgo have detected dozens of black hole mergers, building up a population of known stellar mass black holes. This has revealed surprising features of the black hole population. Many of the black holes are more massive than we expected based on stellar evolution models. Some mergers involve black holes with significantly different masses, while others involve nearly equal mass pairs. And the detectors have even caught a few mergers involving intermediate mass black holes, those in the previously elusive range between stellar and supermassive. Each detection adds to our understanding of how black holes form, evolve, and interact across cosmic time. Each gravitational wave detection tells us something about the black holes that produced it. From the waveform, the specific pattern of the signal, physicists can extract the masses of the two black holes, their spins, how far away they were, and even whether they were actually black holes or something else. The signals last only a few seconds, but they encode an enormous amount of information. As the two black holes spiral inward toward each other, the frequency of the gravitational waves increases, producing a characteristic chirp pattern. The final moments of the merger, when the two event horizons touch and merge into one, produce the strongest signal. The detection of gravitational waves from merging black holes opened an entirely new window on the universe. For the first time, we could observe black holes directly through their effect on space-time itself, rather than indirectly through their effect on nearby matter. The LIGO detectors that made this possible are marvels of engineering, able to measure changes in length smaller than a proton across the 4-kilometer length of their arms. When a gravitational wave passes through Earth, it stretches and compresses space itself by this tiny amount, and LIGO can detect it. We've now described the evidence for the existence of stellar mass black holes and supermassive black holes in some detail. Stellar mass black holes are found primarily by looking for their characteristic X-ray binary signature, where they're actively feeding on a companion star and glowing in X-rays, or by detecting their gravitational wave signals as they merge with another compact object, whether that's another black hole or a neutron star. We've found dozens to hundreds of these through various methods. Supermassive black holes, on the other hand, are found at the centers of nearly every large galaxy we've examined carefully enough, almost universally. They usually have masses of at least 1 million times the mass of the Sun and can be billions of times more massive for the largest ones. We find them by observing the motion of stars or gas near galactic centers, which reveals the gravitational influence of the central mass, or by observing the effects of their accretion disks and jets when they're actively feeding and shining as active galactic nuclei. But there should be something in between these two populations, a missing link of sorts connecting stellar mass to supermassive. Right now, though, the intermediate mass black holes, with sizes between a few hundred solar masses and 1 million times the mass of the Sun, are quite scarce in our observations and detections. We're only in the beginning stages of discovering and confirming these middleweight black holes, and they're proving elusive. A few candidates have been found here and there, some globular clusters, dense collections of hundreds of thousands of old stars orbiting our galaxy and other galaxies, show evidence of intermediate mass black holes at their centers based on the motion of stars in the cluster, stars moving faster than expected without a central massive object. There have also been a few gravitational wave detections that might involve intermediate mass black holes, including some with masses around 100 solar masses or slightly above. Though these are still being carefully analysed and confirmed, and it's not always clear if they count as intermediate mass or just heavy stellar mass. Understanding the growth and evolution of black holes from stellar mass up to supermassive sizes is an active and important area of current research in astrophysics, and searches for these middle mass black holes are actively underway using various techniques, including tidal disruption events, X-ray observations, and gravitational wave detections. Finding more of them would help us understand how supermassive black holes grew so large, so quickly, and how they formed in the early universe when the universe was much younger and smaller than it is today, less than 1 billion years old. What is the ultimate fate of a black hole? Do they change over time, or are they eternal? Well, yes, they certainly can accrete mass upon themselves and get bigger when material falls in, growing over time. A black hole can grow by swallowing gas, dust, entire stars, or even other black holes in mergers. But the question is, how can a black hole die? Can they ever shrink or disappear, or are they truly eternal? To answer this deep question, we need to combine general relativity with quantum mechanics, bringing together the two great pillars of 20th century physics that don't quite fit together yet. The amount of data involved is staggering. Each night of observations generates petabytes of data, so much that it cannot be transmitted over the internet. Instead, hard drives are physically flown from each observatory to central processing centers where supercomputers combine the data. The analysis itself is incredibly complex, involving sophisticated algorithms to account for Earth's rotation, atmospheric effects, and instrumental noise. Multiple independent teams analyzed the data using different algorithms to ensure the results were robust, and all teams converged on the same image, giving us confidence that what we're seeing is real. The Event Horizon Telescope's image of M87's black hole represents a triumph not just of technology, but of international collaboration and data analysis. The telescope isn't a single instrument, but a network of radio telescopes spread across the Earth, from Antarctica to Chile to Hawaii to Spain. Each telescope independently records the radio waves coming from M87, along with precisely timed timestamps from atomic clocks. Later, these observations are combined using a technique called very long baseline interferometry, which essentially turns the entire Earth into one gigantic telescope. According to classical general relativity alone, black holes are completely and permanently dark, perfectly black. Nothing, not even light, ever escapes from inside the event horizon once it crosses. A black hole would be perfectly eternal and unchanging, except for growth through accretion, lasting forever. But this perspective doesn't take into account quantum mechanics and quantum field theory, which introduce some truly intriguing and surprising ideas that change the picture. Stephen Hawking proposed in 1974, in a groundbreaking paper that combined quantum field theory with general relativity in a new way, that when you consider quantum effects near the event horizon of a black hole, something remarkable and unexpected happens. In the intense gravitational field surrounding a black hole, where the gravity is so powerful and the space-time so curved, quantum mechanics predicts that pairs of subatomic particles and antiparticles can spontaneously appear out of the vacuum, out of apparently empty space. This is related to the Heisenberg uncertainty principle, which allows for temporary violations of energy conservation on very short timescales and at very small scales, creating virtual particle pairs that normally quickly annihilate. Normally, in flat space, far from any black hole, these particle-antiparticle pairs, often called virtual particles, would quickly find each other and annihilate each other, disappearing back into the vacuum within a tiny fraction of a second, a time so short that the energy borrowing is allowed by quantum uncertainty, restoring energy conservation. But near the event horizon of a black hole, something different and strange can happen. One particle from the pair might fall into the black hole, crossing the horizon and disappearing, while its antiparticle escapes to infinity, flying away into space. To an outside observer watching from far away, it appears that the black hole has emitted a particle, even though nothing came out from inside the horizon. The particle that escaped was created just outside, never crossing the event horizon itself. This extremely rare and subtle process would lead to the gradual emission of particles from the region just outside the event horizon over very long periods of time. This tiny outbound trickle of particles can be characterized as thermal radiation, meaning it has a specific temperature associated with it based on the size of the black hole, following a black body spectrum like the radiation from a warm object. This phenomenon is called Hawking radiation, named after Stephen Hawking, who predicted it theoretically. Because energy must be conserved overall in the universe, if the black hole is radiating particles away, carrying energy into space, it must be losing mass and energy somewhere to balance the books. Where does that energy come from? The black hole itself. The particle that fell in can be thought of as having negative energy from the black hole's perspective, reducing its mass. The black hole effectively evaporates slowly over time, shrinking gradually as it loses mass. The luminosity of this particle emission, the rate at which it radiates energy, would be proportional to the inverse of the black hole's mass squared. This means that the bigger the black hole, the less radiation it emits, counterintuitively. A more massive black hole has a larger event horizon and a weaker gravitational field gradient at the horizon, a gentler change in gravity over distance, leading to less Hawking radiation production. Since this radiation has the characteristics of thermal emission from a hot body, we can assign it an effective temperature related to its spectrum called the Hawking temperature. To that end, smaller black holes would have a higher Hawking temperature, glowing brighter, resulting in faster rates of evaporation and energy loss. The relationship is inverse. A tiny black hole would be very hot and bright in Hawking radiation and would evaporate quickly, perhaps explosively. A large black hole would be very cold, barely above absolute zero, and would evaporate extremely slowly over incomprehensible timescales. When Hawking first announced his result in 1974, it stunned the physics community. Many physicists initially didn't believe it. How could something come out of a black hole when nothing is supposed to escape? The resolution is subtle. The particles don't actually come from inside the event horizon. They're created just outside it by the quantum vacuum interacting with the black hole's gravitational field. One particle of the pair falls in, and from the black hole's perspective, it has negative energy. The other particle escapes to infinity, carrying away positive energy. The net effect is that the black hole loses mass, while the rest of the universe gains energy in the form of radiation. The concept of Hawking radiation emerged from Hawking's attempt to understand what happens to quantum fields in the curved spacetime around a black hole. In flat spacetime far from any massive objects, quantum field theory predicts that the vacuum is not truly empty, but filled with quantum fluctuations. Virtual particle pairs constantly pop into existence and quickly annihilate, borrowing energy from the vacuum for brief moments allowed by the uncertainty principle. Near a black hole's event horizon, however, the intense tidal forces can separate these pairs before they have a chance to annihilate. For example, a black hole with the mass of our Sun, 1 solar mass, would have a Hawking temperature of about 60 nanokelvins, 60 billionths of a degree above absolute zero, far colder than the cosmic microwave background radiation that fills all of space, which is about 2.7 Kelvin. Such a black hole would actually gain mass faster by absorbing background radiation, soaking up photons from the cosmic microwave background, than it loses mass through Hawking radiation. So it would grow slightly rather than shrink in today's universe. It would take approximately 10 to the 64th power years for such a solar mass black hole to fully evaporate through Hawking radiation alone, assuming the universe eventually cooled enough that it stopped absorbing more energy than it radiated. To put that enormous number in perspective and make it comprehensible, the estimated current age of the universe is about 10 to the 10th power years, roughly 14 billion years or so, 13.8 billion to be more precise. This means it would take about 10 to the 54th power times longer than the current age of the universe for a single solar mass black hole to evaporate completely through this process. That's a 1 followed by 54 zeros times longer, an incomprehensibly vast span of time, far longer than any human timescale or even cosmic timescale we normally consider or can imagine. And for a supermassive black hole like the one in M87, with its 6.5 billion solar masses, the evaporation would take even longer, vastly longer. It would take on the order of 10 to the 102nd power years, a 1 followed by 102 zeros years for such a massive black hole to fully evaporate. These timescales are so vast that they're almost meaningless to our minds, beyond comprehension. The universe will be a completely different place, cold, dark, and empty of stars. All the stars long dead and gone, galaxies dispersed, long before even stellar mass black holes begin to evaporate significantly through Hawking radiation. By the time black holes start to evaporate in earnest, the universe will be in what's called the black hole era, a time unimaginably far in the future when black holes are the dominant remaining objects. Eventually, in the black hole era, perhaps 10 to the 60 power years from now, black holes will be the only remaining organized structures in the universe. Everything else will have either fallen into black holes or drifted away into the expanding darkness between galaxy clusters. At this point, black holes will begin their slow evaporation through Hawking radiation. The smallest black holes will evaporate first, in brilliant flashes of gamma rays. Larger black holes will take longer, evaporating more slowly as the universe grows colder and darker. Finally, in the unimaginable far future, the last supermassive black holes will evaporate, leaving behind only a cold, dark, expanding universe filled with radiation and fundamental particles. These incomprehensible timescales place black hole evaporation in the context of the ultimate fate of the universe. Long before stellar mass black holes begin to evaporate significantly, the universe will have changed beyond recognition. In about 10 to the 14th power years, all the stars we see today will have burned out. The universe will enter what cosmologists call the degenerate era, when dead stellar remnants like white dwarfs and neutron stars are the most common objects. After about 10 to the 40th power years, even these remnants will have either fallen into black holes or been ejected from galaxies as galaxies themselves dissolve. Hawking radiation is obviously a fascinating theoretical concept, deeply important to our understanding of quantum gravity and the connection between quantum mechanics and general relativity, but it does not have any significant practical implications for today's universe, or even for the distant future we can reasonably imagine or observe. The effect is real according to our best understanding of quantum field theory in curved spacetime, combining quantum mechanics with general relativity in a consistent way, but it's utterly negligible, completely undetectable, and unmeasurable for any black hole we might actually observe in our current universe, or any time in the foreseeable future with foreseeable technology. Still, Hawking radiation is important conceptually and theoretically because it suggests that black holes aren't truly eternal, that they can die. In principle, they can evaporate completely, given enough time. When they get very small near the end of their evaporation, in their final moments, they would get very hot and radiate intensely, perhaps even explosively in a final burst, before disappearing in a flash of gamma rays and particles. This raises profound questions about what happens to the information that fell into the black hole over its lifetime. Does it get destroyed forever, violating the principles of quantum mechanics that say information can't be destroyed in the universe? Or does it somehow get encoded in the Hawking radiation and escape over time, preserved in some form we don't understand yet? This information paradox remains one of the deepest unsolved problems in theoretical physics today, connecting black holes to the foundations of quantum mechanics and causing heated debates among the best physicists. Theoretical work continues to push our understanding in new directions. Physicists are exploring connections between black holes and other areas of physics that seem completely unrelated at first glance, such as condensed matter physics and quantum information theory. These unexpected connections are revealing deep truths about the nature of space-time and quantum mechanics. Black holes are teaching us that the universe is stranger and more wonderful than we ever imagined, and every answer we find seems to open up new questions. The future of black hole research promises to be as exciting as its past. New gravitational wave detectors are being built and planned, including the space-based LISA detector, which will be sensitive to lower frequencies and able to detect mergers of supermassive black holes across cosmic distances. The Event Horizon telescope is expanding, adding more telescopes to its network and working to create videos of black holes rather than just still images, allowing us to watch the dynamics of matter spiraling into these cosmic vortexes in real time. Another approach suggests that the interiors of black holes might be connected to the exteriors in ways we don't yet comprehend, perhaps through quantum entanglement or through wormholes in space-time. These ideas push at the very boundaries of our understanding of quantum mechanics, general relativity, and the nature of information itself. Resolving the information paradox will likely require a complete theory of quantum gravity, and understanding what happens to information in black holes might teach us fundamental truths about the nature of space, time, and reality. Recent work on the information paradox has suggested some possible resolutions, though none are universally accepted. One intriguing idea is that information falling into a black hole is not truly lost, but becomes encoded on the event horizon itself, like a hologram. This is related to the holographic principle, which suggests that all the information contained in a volume of space can be represented on its boundary surface. If this is true, then the information doesn't disappear into the singularity, but remains accessible on the event horizon, eventually being released through Hawking radiation in an encoded form we don't yet understand. There's so much more to learn about black holes, so many fascinating aspects we haven't covered here in depth, but I'll leave those topics for other videos to explore in more detail. I encourage you to watch my videos about quasars to learn more about the supermassive black holes that power those brilliant beacons from the early universe, some of the brightest objects we can see across cosmic distances. Watch my video about the Milky Way galaxy to learn more about Sagittarius A star and the supermassive black hole at the heart of our own home galaxy, the black hole we orbit around. Also, watch my videos on gamma-ray bursts to learn about some of the most energetic explosions in the universe, which may be connected to black hole formation when the most massive stars collapse or when neutron stars merge. And explore my videos about the amazing discoveries by the LIGO collaboration, by the Virgo collaboration, and the Event Horizon Telescope collaboration to dive deeper into how we detect these invisible objects through gravitational waves and how we image them directly with Earth-sized telescopes. Since you made it all the way to the end here, watching or listening to this entire journey through the cosmos, this exploration of some of the most extreme objects in existence, you should definitely subscribe to my channel and give these videos some likes to help other people find this educational content and learn about the universe we inhabit. Thanks so much for watching and learning with me tonight, and we'll see you next time on another cosmic journey. Good night and sleep well under the stars.